Hello, class. This is Mr. Hart. And this podcast, we want to start the last lesson in the forces unit, and that is on angled forces. Okay. Now, up to this point, all we've been dealing with was forces that are purely in the horizontal direction and forces that are purely in the y direction. Okay. Now we need to get into what we do if there's an angle. What if there's a force that's not in one of those directions and it's in between those two? Okay. So we're going to have to go back to lesson 3.2 on when we dealt with angled vectors. Okay, we did that because we wanted to be able to do angled forces, which is what we're talking about today. So you'll have to remember these equations that we talked about with vector magnitude and direction. The Pythagorean theorem basically gives you the magnitude of the angled vector, and this equation with the inverse tangent gives you the angle of that vector. Okay. And you can also find the components of a vector by using this equation, where x is the magnitude times the cosine of the angle, and the y is the magnitude times the sine of the angle. Okay? So, let's think about how we do this with the context of forces. Okay? So, because forces are vectors, we can break them down into their horizontal and vertical components. Okay? This makes it convenient because then we can find the vertical and horizontal equilibriums and motions, right? We can consider just the x direction when we're finding equilibrium and just the y direction when we're finding equilibrium and the resulting motions that come from that, okay? So even though we're dealing with angled vectors, we still think of the motion and the forces just in x and y directions, okay? So again, those same equations we used are now going to be applied again, okay? So let's, for example, say that we have a force that's 50 newtons, okay, and it's at a 35-degree angle from the horizontal. Well, again, we can think about an x component like this and a y component like this. Okay, it's basically two forces, one in the x direction, one in the y direction. Okay, so let's find those right now really quick as just a review. Okay, so if we're trying to find the y component, we say y is the sine. It's the magnitude times the sine. So a sine the angle. And x is the magnitude times the cosine of the angle. Okay, so if we take 50 newtons times cosine of 35, okay, that will give us that this component is 40.96 newtons, okay, almost 41 newtons, and then 50 times sine of 35 should give you 28.68 newtons, okay? So make sure on your calculator that's in degrees mode, make sure you get these two values before you get too far into this lesson, because otherwise your calculator will give you a lot of weird angles because it's based on radians. So make sure it's in degrees. Make sure you're getting these same numbers. Okay? So this is what we've done before. We've taken a vector, found its components by using the angle and the magnitude. Okay? But let's look at how this could be applied into a force problem. Okay? Remember those two numbers, 40.96 and 28.68. Okay? So let's say we have this scenario, and this is like the classic physics scenario. I don't know why anyone would actually hang up an ornament this way, but the scenario is you have this ceiling, okay, or the wall and the ceiling in this corner, and you're hanging some object or some ornament by two ropes. One goes directly horizontal to the object, and one goes at an angle to the object. Okay? I don't know why you'd ever hang anything like this, but it's a classic physics problem because it helps us think about vectors. Okay? So basically, we have the same force, 50 newtons, and a 35-degree angle. Okay? So let's think about the forces that are being applied to this object. Okay? Well, obviously we have the two tensions, right? So we can think of this as a force, right? And we can think of this as a force, right? So we got those two forces for sure, and we got the gravity of the object. Okay? So we got this tension, that tension, and the gravity working on the object. Okay? So if this is an equilibrium, which it should be, most ornaments don't, move once they've been hung, okay? we need to balance out the forces. Okay, but this is weird because right now there's no force directly opposing gravity and there's no force directly opposing this horizontal tension. So there needs to be balancing coming from this force. Okay. Now remember those two numbers we just found? We can think of this force, okay, rather than being just one random angled force as being two forces, one in the horizontal direction like this, and one in the in the vertical direction, the y direction like this. Okay? So there's an x component and a y component. Okay? So instead of thinking of this part, we think of this as two vectors or two components in those directions. Okay? Now we need the two numbers we got last time. We found that the x was 40.96 newtons, about 41 newtons, and this was 28.68 newtons, right? So if this is 40.96 newtons and this is 28.68 newtons, then to keep this balanced in equilibrium, the gravity must be 28.68 newtons, and this tension must be 40.96 newtons. Okay? And there we go. That keeps it in equilibrium. And now we have the gravitational force, we have the tension force, and we can solve for the force diagram. Okay? But all we had to do was break this into components, and then we can do these problems like we've done before. Okay? All right, let's do a kind of a more difficult example. All right, let's think about this problem right here. So you have a child being pulled in a wagon, okay? And again, if you think about how you pull on a wagon, you don't just pull it directly horizontal, right? You usually pull up on it a little bit. So you're going to have some kind of angle on your applied force, right? Because you're pulling up on the handle, okay? You get 60 newtons of assistance from the normal force as shown, and you're trying to find the weight of the wagon and the child together, okay? And so we're trying to find this force right here. Now, you might be tempted to say, oh, well, it's 60 newtons here, so it must balance out. It must be 60 newtons there. But again, you got to remember this has components. So to start, let's find the components of this vector. Okay? We don't actually need the x component, right? Because we're not worried about this for this problem. We're focused on the y direction. So let's just find that first. So the y component of this vector is the magnitude of the vector, 350 newtons, times the sine of 27 degrees. Okay? You do that, 350 times sine of 27, you should get that it's about 159 newtons. Okay? So what does that mean? That means if we looked at the y component of the vector, this part right here, okay, that is equivalent to 159 newtons going up. Okay? So now we have two forces in the y direction. We have the 159 newtons going up from this force. We have 60 newtons going up from this force. So the total net force going up in the y direction should be 159 plus 60, okay, or 219 newtons going up in total. Okay? So now that's all the y components going up, so all the y components going down should balance that out. So that means that the gravitational force must be 219 newtons. Okay? So that is the weight of the wagon and the child, 219 newtons. And there you go. Then from there, you could divide by 9.8 if you need the mass or anything else you need to do. Okay, but finding these components is very helpful for these types of problems. So that's one set of example problems that you could have where you're given the vector magnitude and angle. But let's think about what happens if you're not given the vector magnitude and angle. What other types of scenarios could you have? Okay. So now let's think about the other direction. So you may have a scenario where you're working with the forces and you get a net force in two directions simultaneously. So far, usually we just have a net force in the x direction. But what if we have a net force in the x direction and the y direction? Okay. In those cases, we can find the magnitude and direction using those equations that we have looked at before. Okay. So that's going to be the other types of problems we can get. So let's look at an example. Okay, so let's say it's the Spirit Bowl, and you're doing the four-way tug of war. If you've ever had the Spirit Bowl at Orem High, you know how that goes. There's always that four-way tug of war. Okay, and basically they're tugging on that rope, and each side, okay, sophomores, juniors, seniors, faculty, each side's pulling as hard as they can, and these are the relative forces that they get. Okay, well, now we're going to have net force in two directions. Okay, the y direction is not balanced, and the x direction is not balanced. Okay. Again, this is from an aerial view, so we're not worrying about gravity. Okay. But we're not balanced in either direction. Okay. And so we're going to get two net forces. Okay. If we think about it, the net force in the y direction is just going to be these two components minus each other. So that's going to give us 150 newtons going down. Okay. And then these two components minus each other, which will give us what is that? 250 newtons going right. Okay. So in reality, if we're drawing our new diagram, all it would have, if it just was the net forces, would be 250 going this way and 150 going this way. Okay. But it's really weird to describe your net force as components. We want to find the total net force, right? The total net force, magnitude, and direction. So we're going to need to plug that into the Pythagorean theorem. Okay, so net force will be 250 newtons squared plus 150 newtons squared, all square rooted. That will give us that the net force is don't forget to square root, by the way. Should get about 291.5 total force, total net force, 291.5 newtons. Okay, so that's the magnitude of this vector, 201.5 newtons. Okay, and we're going to want to find the direction, and I'll write that equation down in case you've forgotten it, but it's the tangent inverse of y over x, which in this case would be the tangent inverse of 150 over 250. Okay, and that will give us that the angle made to the horizontal is about 31 degrees. Okay, so this angle right here is 31 degrees. Okay? And there we go. So now we found a net force at an angle, okay, for this scenario. Okay, so that's another powerful set of problems we can do is find net forces at angles that we haven't done before. Okay? Let's do one more problem, okay, that has all of this stuff combined, okay, to make sure we got this down. And then I think we'll be good to go on these problems. Okay. So let's say we have this scenario here. So this is what I call a master problem. We would have done this at tables, and we did this one in class at Table Masters. Okay, but it's pretty hard. So we're given relatively small amount of information here. We're given the normal force of the object is 400 newtons. We're given that the mass of the object is 100 kilograms, and we're given that the coefficient of friction is 0.6. Okay, so we're going to need to be able to combine everything we've done up to this point to solve this problem. Okay, and we're trying to find the net force and angle for this arrow right here, this applied force. If you think about this problem, first of all, we're going to need to be able to find the components of this vector, right? We can't just straight out find that force until we know how much x force is needed and how much y directional force is needed. Okay? So in reality, we can think of it as we have two forces being applied upwards, one force being applied to the right and one force being applied to the left. Okay? So this friction force is going to need to balance out with this x force. Okay? Oh, I should state this is an equilibrium. That's an important component of this equilibrium. Okay? So this x force, although it's not drawn to scale, should balance out with this x force. This y force and this y force should balance out with this y force. Okay? So let's find things we can determine. Okay? So we can determine the gravitational force because we have the mass of the object. Okay? So that's just going to be 100 kilograms times 9.8 meters per second squared, okay, which will give us that this is 980 newtons. So we have 980 newtons going down. We can determine that from the mass, okay. We have 400 newtons of normal force, so we can determine the friction by using the F sub k equation, which is just 0.6 times the normal force, which is 400 newtons. And that will give us that the total force going to the left is 240 newtons. Okay, so we got our two forces. Now let's find those components that we'll need for the applied force. Okay, so the x component is relatively easy. If there's 240 newtons going left, there needs to be 240 newtons going to the right. So the x component force will be 240 newtons. Okay, now if there's 980 newtons going down, there should be 980 newtons going up. Okay, but there's 400 newtons from the normal force, which means this force going up will be what's left over, which will be 580 newtons. So to find the total force, we now have the two components. We have 580 newtons going in the y direction and 240 newtons going in the x direction. So we're just going to plug it into the Pythagorean theorem. So 240 newtons squared plus 580 newtons squared, all square rooted. You put that in your calculator. You should get that the net force for this problem, or the total force for this applied force, is 628 newtons. And the angle that it makes is the y direction, which is 580, over the x direction, which is 240. Take the tangent inverse of that. You should get 67.5 degrees. Okay? So this angle is 67.5 degrees. The total force is 628 newtons. Okay? So again, lots of stuff. This is why I always tell my students, you gotta be master builders. There's a lot of things going on that we can account for, and there's a whole bunch of tool sets that we have to solve this problem. Okay, let me just talk you through this one more time just to make sure we're clear on what we need to do. So whenever you have an angled force that you're trying to find, you have to consider it in terms of its components, okay, rather than the force itself. Then, based on the problem, find the other values based on what you know. Friction is the normal force times the coefficient of friction. The gravitational force is the mass times 9.8. Okay? Balance the problem out as stated if it's an equilibrium. Find those two components, and then once you have those components, plug it into the equations we looked at for the Pythagorean theorem and the tangent inverse equation to get the magnitude and the angle. Okay? But that's it. If you can get this problem down, you have everything down in forces. You can solve any type of problem. Okay? But make sure you do the homework. Let me know if you have any questions, and thank you for watching.